All right, so here it goes. Again, the first thing we're going to talk about is the average value of a function on an interval. All right, so now look, you guys have been doing averages since probably middle school or elementary, right? If you have a finite, in other words, a set number of values, it's real simple. You just add up the values and divide by the number of values, and that gives the average, right, of all of those. Okay, but think about it. It's not so easy to find the average of an infinite number of data values, such as temperatures throughout the day, for one example. And so to find those types of averages where there's an infinite number of data values, right, you need calculus, okay? And so if you think about it, this formula should make sense, okay? So to find the average value of an infinite number of values, you integrate the function on the interval, and then basically you divide by b minus a. In other words, you multiply by 1 over b minus a. Okay? And I think when we do some applications with units, you'll understand why that kind of works out the way it does. But anyway, let's look at an example. So suppose I want to find the average value of this function over the interval 0 to 2. Obviously, there's an infinite number of data values, isn't there, in there? Because you can keep adding more and more decimal places and get an infinite number of values. Yes? Right? Agreed? So how do we find the average of all those function values? Okay? So it's real simple. You take 1 over your b minus your a, so 1 over 2 minus 0 times the antiderivative from 0 to 2 of the function. And then when you integrate that using the power rule, don't you get that? Right, when you add one to the exponent, divide by the new exponent, put in the upper limit of 2, subtract what you get when you put in the lower limit 0, multiply by the 1/2 out front that was there, and then you get 4. Okay, so what is that? What is that number 4? What is that? Well, if you think about it, if you could somehow take all of the y values on that parabola over that interval and take the average of them, the average y value would be 4. That's what you're finding. You're finding the average y value. Does that make sense? Okay, good. Okay, can you put all your stuff under your desk for me? All right. Binders too. Okay. All right, so how would you punch this in the calculator? Well, again, because I could ask you this on the calculator part of the next test or the non-calculator part of the next test. And if I give you a function you can't integrate, clearly then you'll have to do it on the calculator. So make sure you could do something like that. It's real simple. I know I don't need to put in the minus 0, but I'm just showing it to you anyway. Okay, so everybody agree that'll do it right there? Yes? Okay, so no big deal. If I give you a calculator, no matter what the function is, just punch everything in very easy. Yes? Okay? All right, now, let's look at another example. Okay, this one's an application. Suppose you want to find the average velocity of a moving object over the time interval 2 to 6 seconds if you have the velocity function. So obviously you want to find the average value of that function, don't you? Right? Now again, there are actually 2 ways to do it, okay? All right, so if you want to find the average velocity, okay, then, okay, so there's 2 ways. Think about that. If you want to find, if you have the position function, okay, then we would use this old formula, that doesn't require calculus. You can just take the change in position over the change in time. Doesn't that give you the average velocity? That's one way to do it, and you'd get the correct answer. However, since you don't have the position function, you have the velocity function, it's better to use what I just showed you and say, okay, the average velocity can be found by taking 1 over time 2 minus time 1 times the antiderivative for the, right, or the integral of whatever you're trying to find the average value of. Aren't you trying to find the average velocity? So wouldn't the velocity function go there in this case? Yes? And then you integrate from time 1 to time 2, which is that. And then from there you can just finish it, right? So here we go. Obviously, when I integrate, I get 4t squared over 2, which simplifies to 2t squared. Put in the 6, and that gives you what? 72 minus what you get when you put in the 2, which is 8. So what do you get? 64 over 4, which is what? 16. 16 what? What would the units be in this case? Well, we don't have units, so. Now again, this is average what? Velocity, right? Okay, so suppose V is in meters. Well, V is in meters, then the answer here would be what? 16 what? Meters per what? Per second? Yes? So again, so if you have the velocity function, you can just do it this way. And that'll give you the average velocity for the object over that time interval 2 to 6 seconds. If you have the position function instead of the velocity function, well, then you can find the answer doing it this way instead, right? Without calculus. Understand? So on the AP test, depending on what they give you, you might have to do it this way or this way. So you should know both ways. Got it? Good? Okay. All right, here's another application. Suppose you want to find the average circumference of all circles whose radii range from 2 feet to 5 feet. You want to find the average circumference of all of those circles. Obviously, there's an infinite number of circles in there, isn't there? Yes? If you talk about decimals and all that, right? There's an infinite number of circles, such circles. So you have to use calculus to do it, because there's an infinite number there. Okay, and so to do that then, what are you going to do? The average circumference can be found by taking what? What do you think? 1 over what? How do you think this would set up? You tell me, guys. What would I do? Sam? So 1 over what minus what? Quick. 5 minus 2 times the antiderivative from what to what? 2 to 5, yes? And again, what are we trying to find the average value of? The circumference of a circle. So shouldn't the formula for the circumference of a circle go right here? What is it? 2 pi r. Then obviously you're going to integrate with respect to r, since that's the variable. Yes? And that's it. Everybody agree? So if you find the value of that integral, it'll give you the average circumference of all such circles. Got it? So let's do it. Obviously, when you integrate, you get 2 pi r squared over 2 from 2 to 5. These cancel. You can put in the what? The 5, and that gives you what? 25 pi minus what you get when you put in the 2, which will give you what? 4 pi. So you got what? 1/3 times 21 pi, which is what? 7 pi. And so if you want to make that more meaningful, you can get a decimal. 7 pi is about 21.991 feet. So that's 29.91 or 991 feet is the average circumference of such circles. Got it? Yes? All right, so I just showed you 3 different types of problems. Pretty easy, right? If you know the formula, that's pretty easy. Okay. Now, next page, not going to be so easy. Oh, okay. Well, one more semi-easy one before I go into something more tricky. Okay. All right, so how would you find the average value of a piecewise function? How would it change? Well, I know the mistake you're going to make, and that's why I'm showing you this example. You would still put the 1 over the 2 minus the negative 2 out front, and then to integrate, wouldn't you have to do the integrals separately? The first one goes from what? Negative 2 to what? Well, this function is good for x is less than 0. So wouldn't you need to first integrate from -2 to 0, and then add what you get when you integrate from 0 to 2, and you're integrating the other function in that case. Okay? And then when you're done integrating, that's when you multiply by the 1 over b minus a out front. The mistake you would make is to, do 1 minus 0 minus -2 here, and do 1 over 2 minus 0 here. That would be incorrect. That would give you the incorrect answer. So don't do it. Okay? Integrate like this, and then at the end, multiply by 1 over your b minus your a, which is 1 over 2 minus -2. Understand how to integrate something like that and handle that to find the average value? Okay. All right. This, I believe, is the last new theorem of the year. You must know it because it's tested pretty heavily on the AP exam. Remember you had the mean value theorem for derivatives? Do you remember that, where it said somewhere on the interval the slope at some point has to be the same as the slope of the line through the endpoints of the interval? Do you remember that? That was the mean value theorem for derivatives. This is something else. This is a mean value theorem for integrals. Okay, so let's talk about it. It's related to what I just went over. And so basically, once you find the average value that I just did several examples of, okay, and you get this, you get some value here. Okay, you get this number, right? This is some number, isn't it? Yes? Once you get that number, which is the average value of the function on the interval, the mean value theorem for integrals states that what? That the function must take on that average value at some point in the interval. Okay? Okay, so here's basically how the theorem is stated. Okay? Word for word. Are you ready? Okay, again, this only works if f is a what? Continuous function. So if that's true, then you can apply the mean value theorem for integrals, and the theorem says then the following must also be true in all those instances. That there must exist an x value c on the closed interval a to b such that the y value at that x value is equal to the same as the average value on the whole interval. Okay? Again, so another way to put this is that there's a point on the graph of f where the y value is the same as the average value, as the average y value. Okay? All right, on the whole interval. Okay, that's one way to look at it. Now, there's another thing you need to know, and this is a geometric way of interpreting the theorem. Okay, now again, I know this is going to get confusing, so please watch. And again, this only works for positive functions. Okay, if you use the number of c that's guaranteed to exist, and if you draw a rectangle all the way from a to b with a height of f of c, that rectangle will have an area that's equal to the area under the curve. Okay, I know it's getting very complicated, but hopefully after I do an example, it'll make some sense to you. Okay, so the bottom line is this. First thing I got to make sure you understand is that f of c is the what? F of c is the what? The average value. That's one thing you got to note here. Okay? F of c equals the average value on the whole interval. Yes? Okay, so once you have that average value, and I showed you how to find it a minute ago, use that as the height of the rectangle, and then the width will obviously go from a to b, so the width will be just whatever the length is from a to b. Okay? So aren't you going to have a rectangle, right? Height times width, and that area of that rectangle will be equal to what? The area under the curve, which is just the antiderivative of that from a to b. So this is this basically is the rectangle area, and this is what? The area under the curve. Yes? So what the theorem says, another way to interpret the theorem is that the area of this rectangle that I just talked about will be equal to the area under the curve. All right, let me do an example. I think it'll make a little bit more sense. Okay? So here we go. All right, so I'm going to use example 1 just to save us some time. Okay, so going back to example 1, we found that the average value of that parabola function or quadratic function over the interval 0 to 2 was what? was what? 4. Are you with me? Do you remember that from example 1? All right, so let's take it from there and let's apply the mean value theorem for integrals. First of all, can we even apply the mean value theorem? Yes. Why? Because this is a what? Continuous function. That's all you need is a continuous function, and the theorem will apply automatically. Okay. So according to the theorem now, something else must happen. And what is it? Well, first of all, it says there must exist a value c, right? Where what? Where what? The y value at that x value is equal to the what? Average value. So what I'm going to do is I'm going to take the function, which is 3x squared, okay, plug in c, and I get 3c squared instead of 3x squared, set that equal to the average value, and then solve for c. So what do I got to do algebraically to solve that for c? Divide both sides by what? 3, and then take the what? Square root of both sides, and even though you get plus or minus, I'm only going to keep the positive one. Why? Because I'm only on the interval what? 0 to 2. Okay? Okay, so what I just found was the x value on the interval 0 to 2 where the y value is the same as the average value on the whole interval. Are you following me? Yes? Okay, then I said there was that geometric interpretation that you can also look at. Okay? And so, again, I just said this a second ago, right? This is what I just said a second ago, that at that x value, the y value will be the same as the average value, which is 4. Okay, that's one thing. The other thing is what I was talking about at the bottom of the last page, which is this. If you find the area under the parabola from 0 to 2, everybody agree that's what I did here when I highlighted this black area? Yes, I just found the area under the curve. Okay, so also according to this theorem, that area should be the same as this area right here. And again, where did I get that rectangle from? How did I get that rectangle? Well, what I did is I used the average value for the height, which is what? 4. And then I just drew the rectangle all the way from A to B, in other words, from 0 to 2. So this is clearly what then? From here to here, it's what? 2. So by the way, what is the area of that rectangle? 8. Isn't it 8? 4 times 2? So guess what the area under the curve is? 8. Understand that these two are equal? Yes? Okay, so it's a lot, but I think if you take it a little bit at a time, it's not too bad, right? It's just a lot of new stuff to know. Any questions on this? No? Are we good? Told you it gets harder. I don't think there's anything too easy the rest of the year except one day, which is slope fields. Slope fields aren't too bad. But other than that, I don't think there's an easy section the rest of the year, as you can see already. Okay, so you better be putting in more effort than you did first semester, not less. Don't go getting senioritis on me. Okay? You definitely can't afford that unless you want to bomb this second semester, which I know you don't want to. Okay? You had your chance to get into regular calc first semester, and some of you said, no, I'm going to stick it out. Well, if you're going to stick it out, you better give me more effort. Okay. Anyway. All right. Now, so that was section 6.5. Okay, we're done with 6.5. Now we're moving into section 7.7, which would obviously be something totally different. It's not even in the same chapter. Are you ready to switch gears and do something totally different now in chapter 7? Okay, here we go. So this is the last thing I'm doing today. All right, now I know we all know how to find the exact area under the curve. And so you're going to probably ask me, well, then why are we going to go back to approximating the area under the curve? Well, the only reason is because I didn't do this back when I did Riemann sums because it was in a totally different chapter. And so I'm just kind of picking up the pieces that I didn't cover and just kind of sticking them together. So there's no real good reason why I'm going back to approximations, but I am. Okay? So even though you all know how to find the exact area under the curve by integrating, can I please go back to approximating the area under the curve for one more day or a half of a day? Can you handle that? Okay? All right, so I just didn't want to confuse you. All right, so do you remember when I wanted to find this area under the curve right here? The very first day we talked about area under the curve, what we did is we found Riemann sums by finding these rectangle areas and then adding them up. And we said, okay, that's nothing more than an approximation for the yellow area. Do you remember that? Okay, well, obviously I did Riemann sums, which were rectangles. Okay? And how did I do it? I did what? Length times width plus length times width and so on for however many rectangles. Yes? And again, how did I get the widths again? How did I get the widths? By taking what? Delta x. And what was delta x? How? How did I get delta x? By taking b minus a and dividing by the number of rectangles. You remember that? And then the lengths or heights of the rectangles came from plugging the endpoints into the function. And again, sometimes I use the endpoint, left endpoint, sometimes I use the right endpoint, sometimes I use the midpoint. Do you remember all that? Okay, so that's just a quick review of finding Riemann sums, which were simply rectangle approximations for the area under the curve. Do you remember all that? This is all review. This is nothing new. All right, now we're going to move into something new. And the only difference is, instead of using rectangles, I'm going to use what? I'm going to use what? Trapezoids. Okay, so this is the last new thing you got to know today. It's not too bad. I don't think it is, at least. Now, early on, it's going to be a mess, but then I'm going to clean it up. Okay? All right, so here we go. So here's what I did. I took some random curve from A to B, and by the way, instead of using A and B, I could also use x of 0, right, for the initial x value, and then x of n for the last x value. Same thing, right? So A is the same as x of 0. B is the same as x of n. Okay. So what I did is I marked the endpoints, the y values on the endpoints of each subinterval, assuming I'm going to use 4 subintervals. So again, everybody understand what I did? There's my first subinterval. There's my second subinterval. There's my third subinterval. So I'm using 4 subintervals. Are you with me? Okay. And so instead of drawing rectangles on those subintervals, what did I do here? I connected these y values, and that gave me a trapezoid. Isn't that a trapezoid? Then I connected these 2 endpoints on the second subinterval, and I got this trapezoid. Then I connected the y values on the endpoints of the third subinterval, and I got the third trapezoid. And then here's my 4th trapezoid. Everybody agree those are trapezoids, not rectangles? And so if I take each trapezoid area and add them up, that'll give me an approximation for the area under the curve. Everybody agree with that? All right, so let's talk about how that will set up, okay? All right, so the width, in other words, the distance from there to there, there to there, there to there, there to there, can be found the same way as I did with rectangles, right? Just by taking b minus a over n. Okay, instead of n being number of rectangles, now n is number of trapezoids, right, or subintervals. Are you following me? Yes? All right, now watch. It's going to be messy. Here it goes. All right, so to approximate that area under the curve, instead of a bunch of length times width plus length times width, instead I'm going to have a bunch of what? Of these formulas. What are those formulas? Those are the formulas from geometry for a what? For a trapezoid. Okay? All right. How do I get the, by the way, I think it'll be easier if I back up a minute. Okay, if I have a trapezoid like this, or like, you know, you can turn that sideways if it makes more sense. The bottom line is these are your base 1 and your base 2. The base 1 and base 2 are the parallel sides. Everybody agree? And then what's the h? The h is the what? The perpendicular height in between the bases, yes? And so everybody agree that if you look at it the other way, that the delta x's are your heights now, aren't they? Aren't they? Yes? This is your h. As long as this is perpendicular, which it is. Are you following me that your h's are your delta x's and your y values on the endpoints of each subintervals are your b1 and your b2? Would you agree with that? Yes? Okay? Okay, so with that in mind, then I think you should see where this formula comes from. b1 and b2 are your what? F of x of 0 and your f of x of 1, yes? Yes? By the way, because again, you're going to use those 2 x values, plug them in to get the y values, and that'll be your height 1 and your height 2, which is your b1 and your b2. Are you following me? And then how about the second trapezoid? You're going to use a what? x1 and what? x2. How about for your third trapezoid? You're going to use what? x2 and what? x3. How about your fourth one? x3 and x of n. Are you following me? So, and then again, what's the h? The h's are all what? The h's are all what? The h's are all delta x, aren't they? Are you following me, guys? And so on. All right, now what do you notice here, guys? What do you notice about each one of these? What do you notice about that whole formula? And then this whole formula? And then this whole formula, and so on. They all have a what? They all have a what that I can pull out? They all have a half. Somebody agree I can pull that out? What else do they all have? A delta x. I pulled that out. And then when you're done pulling that out, what do you have left over in brackets? Well, you've got an f of x of 0, but then you have what? Didn't you use f of x of 1 twice? Once for the first trapezoid, once for the second trapezoid? So notice how I have one f of x of 0. I've got two f of x of 1s. And then what? What about x of 2? Isn't f of x of 2 used twice? Once for the second trapezoid, once for the third trapezoid. So I've got two of those, and so on, until I get to the end, and then I'm only going to have one what? One what? F of x of n. Are you following me? I know it's confusing, but I'm trying to explain one little piece at a time. Are you with me? Okay. And then finally, you can replace delta x with what? Delta x is just what? Your b minus your a divided by n, which is the number of trapezoids or subintervals. Are we good? Jason, is this making sense? You sure? Okay. All right, so when you put all that together, if I replace this delta x with b minus a over n, don't I get 1/2 times that, which turns into that, and then times all of this. Okay? And so, again, this is nothing more than a what? An approximation for the area under the curve. Okay? All right, so at this point then, if I ask you to use the trapezoidal rule, you got two choices. Number one, you could do what? Memorize and use that formula that I just explained where it came from. Okay, that's one thing you can do. Or, if you want, if it's possible, you can just draw what? Draw the trapezoids and then just find each individual trapezoid area on your own like you did back in geometry and just add them together. So, all right, so let me explain that. Are you ready? Are you ready for me to kind of summarize and explain what you're going to do now with all of this? Okay, so what if your subintervals are not equal? Well, then you cannot use rule 1, okay, or method 1. You cannot use this memorized formula unless the delta x's are the same. And so you'll only use if what? If what? Your delta x's are equal. Yes? Okay, so that's the only time you can do it that way. Is that clear? Yes? Okay, so what if you don't have equal delta x's? Then what? Then you can use this way. All right, now let me ask you something. Can I always just use method 2? Yes or no? Sure, as long as you're able to imagine or draw the trapezoid, you can always just use the easy method. But I needed to show you at least the first way in case it ever shows up in the future. Okay? So the bottom line is you can always use this way. Right? But if you have equal with subintervals, you can also do it the other way. It's basically the same thing. It's just using different symbolism, isn't it? Yes, but once you pull out the delta x, the first method requires the delta x to be equal. The second one obviously doesn't, because in each case you're going to put in whatever the height is, which are your delta x's on each subinterval. So this way it doesn't really matter if the h's are the same. The top way it matters because you pulled basically the delta x out to get that formula. Do you understand what I'm saying here? It's confusing, I know, but I think the examples are actually pretty easy. Okay? All right, so here we go. All right, so hang in there. Yeah, I mean, the rest of it won't take too long. I'll be done in 15 minutes or so. Okay? All right, so here we go. All right, I have to do at least one where you use the rule, okay? Just so you can see one time how it works. And then after that, I'll let you do it any way you want, okay? All right, so here it goes. So suppose I want to approximate the value of that integral. Now, obviously, you could actually do the integral and get the exact area, but that's not what I'm trying to do right now. I'm going back to approximating for one day. Are you following me? Okay, so let's find the approximate value of that integral. In other words, I want to approximate this area from what? Isn't that what the sign looks like? I mean, I didn't draw the rest of it, but basically you're just looking at a piece of the sine function that goes up and down like that. Everybody understand what you're looking at there? So I'm looking at the piece of the sine function that goes from what? 0 to what? Pi. Everybody see what you're looking at? So instead of finding that exact yellow area, I want to approximate it using the trapezoidal rule with how many trapezoids? 4. Okay, which way do I want to do it? Do I want to do it the geometry way or the memorized way? The memorized way. Okay, so here we go. All right, so again, even though you're memorizing the formula, you should have a good idea where everything comes from to help you set it up. Are you ready? Okay, where does the delta x come from if you're using equal width subintervals, which is required if you're going to use the memorized rule? You're going to take what? B minus a, which is what? Pi minus 0, which is pi, and divide by the number of trapezoids, which is 4. So everybody agree that our widths, in other words, from here to here, it's going to be what? Pi over 4. From here to here, it's going to be what? Pi over 4, and so on. Do you agree? Those are our widths, which in our, I'll come back to that in a minute. Okay, those are my widths. Okay. So, and then, now what else do I need? Don't I need x of 0, x of 1, x of 2, and so on, right? So this is x of 1, this is x of 0, I should say. This is x of 1, this is x of 2, this is x of 3, and this is x of 4. Everybody with me on that? Yes? Okay, and so, all right, are we ready then to do it? Okay, so here we go. So, isn't this, to approximate this integral, again, notice that's an approximation symbol. I've got to find all of that, and that'll give me the approximation for the area under the curve using 4 trapezoids of equal width. Make sense? Ready? Here it goes. All right. So real quick, I need to put what? B minus a, which is pi minus 0 over 2 times n, which in this case is 2 times 4. All right. Now, how do I get f of x of 0, guys? Well, what is x of 0 right here? What is it? 0. And so don't I just find f of 0? Okay, what's next? I got to find what? F of x of 1. What's f of x of 1? Well, what is x of 1? What is this x value right here? It's pi over 4, isn't it? So that's 0. This is pi over 4 right here. And so don't I need to find f of x of f of pi over 4, I should say? What's the next function value? In other words, what's this next height? F of x of what? What is it from? What is this x value right here? Pi over 2. Just going to plug pi over 2 into the function to get that height, yes? And then what's the next one? 3/4 pi. So you're going to find the y value, in other words, f of 3 pi over 4. And then finally, what's this x value? Pi. Okay, everybody see what I'm doing? Okay, so what I did here is I just plugged 0 into the function, so that would be sine of 0. Here I just plugged pi over 4 into the function, which is that. Here I plugged pi over 2 into the function, which is that, and so on. Are you getting the hang of this? And so what is the sine of 0, guys? Quick. 0. What's the sine of pi over 4? You should know it. Pi over 2, or square root of 2 over 2, I should say. What's the sine of pi over 2? You should know it. 1, and so on. And so after you figure all that out, add all that up, you get that, and then multiply by this, which simplifies to pi over 8, and you punch it in the calculator, and that's the approximate area under the curve. Not too bad, is it? No. Now, am I going to make you memorize that rule? I don't think so. I don't think so. As long as you can use it, I'll be good. Or at least, and recognize it, right? Like if it shows up on the AP test, I'm guessing it'll be in there to where you got to at least recognize it, not really memorize it. I mean, there was a problem many years ago where you had to use this rule. But that was a long time ago. Every trapezoid problem I've seen since then, you can actually do the easy way, the geometry way. Okay? So I think on the homework tonight, I make you use the rule maybe twice. And after that, you can do it the easy way. Fair enough? Yes? Okay, so here we go. All right, so let me do example 6, and we only have one page left. Here we go. Okay, once you see this is actually pretty easy. All right. So again, this is more like what I've seen the AP problems look like in the last 10 years. Okay? Are you ready? With me? Okay, here it goes. All right, so they say f is a continuous function, so automatically you can use the trapezoidal rule, yes? On the closed interval 2 to 8, okay? And instead of giving you the function, or instead of giving you a graph of the function, they simply give you what? A table of some random points on the function. Are you with me? Okay. All right, so now, look, instead of using equal subintervals, they give you the specific intervals you want to use. And by the way, the first subinterval goes from 2 to 5. How wide is that? 3. The second subinterval they want you to use goes from 5 to 7. How wide is that? 2. The third subinterval goes from 7 to 8. How wide is that? 1. So even if you wanted to, you couldn't use the memorized rule, because the memorized rule requires what? Equal subintervals. So you could not, everybody agree you could not do it this way even if you wanted to? You could not? Agree you cannot? Okay, good. All right, so we're going to have to do it the easy way, which is the geometry way. Are you ready? With me, Max? Okay, here we go. All right, so what are we going to do? What are we trying to approximate, by the way? We're trying to approximate the area under the curve from 2 to 8. So here it goes. All right, so ready? Very easy. Basically, you're going to do 1/2 B1 plus B2 times H. So all I'm doing is the geometry way. Everybody agree? Even though it's the same thing, it's easy to understand this way, isn't it? Okay. Everybody agree that's what I need to do? I've got 3 subintervals, so I need 3 trapezoid formulas. Should be writing this down. I see a lot of people just sitting there not writing it down. Write it down. I'll wait for you. Ready? Okay. Notice I'm putting a bunch of blanks in that I'm just going to fill in one at a time. Are you ready? All right, here we go. All right, so for the first subinterval, where does it go from? From where to where? First subinterval goes from where to where? Come on. 2 to 5. So you're looking at that subinterval right there. What's the height? In other words, what's the width? Remember, the height in this case is the width, right? When you turn the trapezoid sideways? Yes? So the height is what? 3. Right? Because you're going from 2 to 5, that becomes the height. Remember that? I explained it right here. That when the trapezoid is like this, the distance from here to here, your delta x is your height, your perpendicular height between the 2 parallel bases. Are you following me? Do you remember that? Yes? Yes or no? Okay, and then what's your B1 and your B2? That would be your what? Your y values on the interval, right? Isn't it your B1, your B2? So what would it be? 10 and what? 30. Isn't this easy? Okay, the next subinterval goes from what? From 5 to what? 7, like that. And so how wide is it? In other words, what's the height? 2. What's your y values? In other words, what are your B1 and your B2? 30 and what? 40. Everybody agree? You can use the 30 and 40? And then how about the last one? What's the height? Quick. Well, what's the h? 1. And what's your B1 and your B2? Well, you're going from 7 to 8, so that would be what? 40 and 20. Okay, so just add all that up, and what do you get? Let's see. Okay, so what do you get? Help me here. By the way, this is an approximation, so make sure you keep it a wavy equal sign. Let's see, 120 times half, that's 60, plus 70, plus what? 30? What does all that add up to? 160? Yes? Okay, so that's an approximation for what? The area under the curve. Is that clear? It's not the exact area under the curve. It's an approximation for the area under the curve from 2 to 8. Isn't it? Yes? It's a trapezoidal approximation is what we call that, right? All right, last page. All right, this will go semi-quick, I think. Let's see. All right, this is an old AP question. Okay, they gave you both a graph and a table. They didn't have to, but they did. They could probably given you one or the other, and you would have been just fine, hopefully. Yes, but they gave you both of them. But just understand that sometimes they're only going to give you that. Sometimes they're only going to give you that. This is an older problem, which is why I think they gave you both. Now they're making it harder on you. Okay, by not giving you both of them. But anyway. All right, so no matter which one they give you, you should be able to figure out the answer to this question. So what does it say? This is the what? What is this a graph of? The what? Velocity function. And then what they did is they highlighted some points and they gave you the points in the table as well. Are you with me? Okay, and so this is the velocity of a car traveling along a straight road over the time interval 0 to 50 seconds. And again, these give you the velocities at random times. Yes? Yes? On that interval. Okay. So we want to approximate the area under the velocity curve from 0 to 50. Are you ready? Are you ready? Now, how do I want to approximate it? With a what? Riemann sum. What's a Riemann sum? That's the sum of the rectangle areas, not trapezoids, yes? So we're going to go back now to Riemann sums for this one AP problem, okay? All right, so here we go. All right, so then, okay, now, how many subintervals are we using? How many? 5. Equal with or not? Equal with? Are they equally wide or are they not? Yes, equally wide. Okay, so, all right then. So you're going to have length times width 5 times. Everybody agree with that? Length times width 5 times. So you have 5 rectangle areas, yes? Okay, and they're equal width. So how can I figure out the width, guys? How can I figure out the widths? Well, I'm taking what? B minus A over N, yes? Which in this case is what? 50 minus 0 divided by how many? 5, and that gives you what? 10. So everybody agree they're all 10 units wide? Yes? I'm running out of space. Sorry, guys. Okay, so I'm replacing all the widths with 10. And again, you don't need to draw them, but if it helps, and since they gave you the graph, I might as well just show you at least a couple of the rectangles. So again, if you take the 50 and you split it up to 5 equal parts, each one's going to be 10 units wide. So you agree that's the first subinterval right there from 0 to 10? And what type of a Riemann sum am I doing? Is it a right Riemann sum, a left Riemann sum, or a midpoint Riemann sum? What kind? Midpoint. So how am I going to get the height of that first one? I'm going to go to 5, right? Isn't 5 the midpoint? I'm going to follow it up till it hits the curve, and I get that as the height, right? V of 5 is the first height? Yes? Are you following me? Okay, let's do the next one. The next one goes from what? 10 to 20. And again, the midpoint is 15, so I follow 15 up till it hits the curve, and I use that y value for the height of my second rectangle. Here's my third subinterval from 20 to 30. The midpoint is 25. Follow 25 up till it hits the curve, and use that y value as the height of the third rectangle. Do you understand what I'm doing, Sam? Yes? Okay. All right, so here we go. All right, so you could draw the next two if you want, but I think 3 is good enough. Okay. So how do I get that first height? Look at it, or think about it. Wouldn't it be V of 5? What's V of 5? What's V of 5? Because this is my first subinterval, right? So what's V of 5? 12. So you agree that'll be my first rectangle length or height? What about my second one? It'd be V of what? Yeah, because I go from 10 to 20, so my midpoint there is 15. So agree I use 30, and doesn't that look like it's 30 for that second height? Yes? Are you following me? My next subinterval goes from what? 20 to what? 30, so the midpoint is 25. Followed up till hits the curve, you'd get 70, wouldn't you, for the height? Okay. What's the next one? You tell me. Come on, 81, and what's the last one? 60. Okay, so let's add all that up. Did anybody do it for me already? Let's see, 120, 420, 1120. You can add them. Somebody's got a calculator going for me. Can somebody do it?
It's 25.
2530. Thank you. Now, units are extremely important. I haven't seen a question like this in about 7 or 8 years without having units on it. And without units, you're not even know what that number even means. So you have to put units. What are the units? Think about it. Think about it. You're finding area. What are the units? Okay, if you just think of this as simply length times width. What are the units from here to here? Well, it's time, so it would be what? Let's just take one of these rectangles. What are the units from here to here? What is it? Well, it's time on the x-axis, so it would be what in this case? Seconds. What are the units on the heights? Well, yeah, the y values are velocities, aren't they? So aren't the y values velocity values? So the units from here to here would be what? Feet per what? Feet per second. And so when you find area, so to speak, you're finding those units times those units. And what's feet per second times seconds? Feet. That makes sense. I mean, I've kind of said this in the past, haven't I? Like when you integrate feet per second, you get feet. So when you find the area under the curve, you're integrating, right? So when you integrate feet per second, you get feet, yes? And again, the reason is because when you're finding the area, technically you're multiplying the y units by the x units. And when you multiply feet per second by second, those cancel. So the answer on this is feet, isn't it? All right, now by putting the units, I think you're able to put meaning behind what you just found. What is feet? Feet is a unit of what? Distance. And so you just found a distance. So what distance did you find? Well, you can say on the interval 0 to 50, the car did what? The car what? Traveled what? 2,530 feet. Let me say that again. In this case, isn't distance traveled the same as displacement? Technically, I just found displacement, but why can I also call it distance traveled? Because it's what? It's all what? Positive. So because everything's positive here, this is one of those problems where distance traveled is actually the same as displacement. So if part of this curve was under the x-axis, then you could what? No longer call it distance traveled. It would just be what? Displacement. Do you understand? And then what if you wanted to actually find distance traveled instead of displacement? What would you have to do? You'd have to take the negative area and make it what? Positive, and then add that to the positive area. And then at that point, it would become distance traveled instead of displacement. Are you following me? Yes? But in this case, since everything's positive, displacement happens to be the same as distance traveled. Okay? All right, one more and we're done. Can you handle it? Now, this is a really good problem. This is like some of those nasty calculator questions that they've been putting on the AP test for the last 8 to 10 years. Okay? All right, so here we go. Last one. Do this and we'll be done. All right, so what is this? This is what type of a function? Gives you the what? Gives you the what? Temperature. So what are the units on those values? The units on those are what? Degrees what? Fahrenheit. So make sure you look at the units to get some understanding of what you're finding. Are you ready? All right, so the first thing I want you to do is what? Graph it. So here we go. All right, so there's lots of things you need to know when you graph something like this, and I'll talk about them as I run into them. So the first thing I'm going to do is just type it in. And by the way, to keep this clean, make sure you use the fraction bar, which is under alpha y equals, isn't it? Just to keep it nice and clean without having to put a million parentheses in there, right? Okay, so there's a couple, oh no, I don't want the parenthesis there. I want the parenthesis on the outside, right? Okay, so a couple things here, guys. So obviously you want to make sure it's entered correctly. Double check it. Okay, looks good to me. The next thing you want to do is make sure in what mode? Radian, because there is a trig function, right? I am in radian mode, that's good. Okay, and then the first time you graph it, because there's a trig function, if I were you, I'd hit zoom what? Z what? Normally I hit zoom Z standard for starters, right? But when there's a trig function, I like to start with zoom Z trig. Okay. All right, so that's the second thing. The first thing was radian mode. The second thing is use zoom Z trig. The third thing is change your what? Change your what? Interval. So you're only looking at the interval you want, which is 0 to 24. Okay, so here we go. Okay. Don't worry about your scale. Okay. All right, now I don't see anything, so it's probably way above the screen, yes? Everybody agree? So, I don't know, let's make the Y max, I don't know, let's try 50. I don't know if that's enough, but let's try that. Oh, by the way, they kind of gave you a hint here by saying go up to what? Going up to what? 100. But that would have been my next try anyway, wouldn't it? 50 didn't show up. Try 100. Yes? That was going to be my next try anyway. Okay. If that didn't work, I'd probably try, 400 or 500. That doesn't work, I'll probably try 1,000 or a couple thousand, right? Just keep playing with the window till you see what you want to see, right? Okay. All right, there. We finally got something showing up. Okay. So at this point, I think I've got the window I need. Yes? Okay. So now hold on a minute. Instead of guessing what these y values are, I can make that grid. Okay, it's been a while since I did it, so I might have to look for it. Let me see. I think it might be under, see, mode? No. How about format? Yeah, there it is. It's under format. See, right now I got the grid off. I can turn the what? Grid on. You following me? Yes? And in order to use a grid, you're going to have to go back and change the what? The what? The scale. So I want to go up by what? 6s instead of 1.5? Okay, so if you turn the grid on and you change the scale, that'll make the grid match whatever scale you choose. And everybody understand why I chose 6? Because that's the scale on the graph that they provided for you? Yes? Okay, and then just hit graph. And by the way, I can also choose a scale on the y's. Can I? So let's go back to window. What do I want my y scale to be? 10s? Yes? And by the way, they didn't start at 0 and go up to 100. They started at what? 60. So everybody see how I'm changing this to match the scale? Everybody see what I'm doing? Yes? Okay, and so anyway, I think you can see what's going on now. It starts here, right? Goes like this to there, and then goes to what, here? Then goes to here. and then finishes off here, doesn't it? Yes? Everybody agree? Okay? All right, so now be careful here. Okay, it says approximate this. In other words, I want to approximate this yellow area, yes? I mean, there's the exact area, right? Whatever that yellow area is, that's the exact value of the integral, isn't it? But I don't want the exact value. I want to what? Approximate that area how? How do I want to approximate that area? Using what? A what? Right Riemann sum. Using what? 4 subintervals, equal length or not? Equal length. Okay, so the first one's going to go from what? 0 to what? 6. And how am I going to draw the height? By using the what? Right end point and following it what? Up till it hits the curve? So everybody agree that's my first rectangle? Remember, Riemann sum is a rectangle approximation. Okay, and then here's my second subinterval. Again, use the right end point, follow it up till it hits the curve, and use that as the y value of my second rectangle, yes? Or the height of my second rectangle, and so on. Third one, fourth one. Okay, are you ready? All right, so obviously I'm going to have what? Length times width plus length times width plus length times width plus length times width, yes? Okay, so here we go. All right, so here we go, guys. Real quick. All the widths are what? Quick, quick, quick. 6. Okay, what about the first rectangle length or height? What is it? 80. What about your next one? What is it? 90. What about your next one? What about your next one? 70. Okay, so since somebody add all that up for me, tell me what it is. 1920. Thank you. Now again, what are the units? This is tricky. What are the units? Well, again, you're finding area, and actually finding the area using rectangles actually makes it pretty easy to figure out what the units would be, because these are what? Hours? Isn't the hours? Units from here to here hours? What are the units from here to here? What is it? Degrees. And so when you multiply that by that, you get what? Degree hours. Okay, degree hours. Maybe it doesn't mean much to you, but those are the appropriate units. Yes? Degrees times hours, or just degree hours is the way we say it. Yes? Good? All right, now, what is this? Does this say anything about approximating? No. If it said approximate it, then you could use this and just multiply by 1 over 24, right? But it didn't say approximate it. It's implying you want to find the what? Exact value of that? Yes? And so how would you do that? How would you do that? Well, you can do it on your home screen, can't you? Sorry, too bright. Math function integrate. Whoops, alpha function. Okay. And I already got it in y1, don't I? So I can just make it easy on myself and put y1 there, right? But do you agree? All right, so what do you get? 80. Now again, tricky, tricky, tricky. What are the units on this? Well, first of all, what is this, guys? What is this? What are you looking at? Can't I think of it like this? Isn't 24 the same as 24 minus 0, which matches my interval, doesn't it? So just by the way it's set up, what is that? That should equal the what? The average value of what? F of t. And what is f of t? The average, what is f? F is the what? Temperature. Doesn't this formula give you the average value of whatever function is sitting right there? Yes? Yes or no? Yes or no? Yes, it does. So what are the units of the function sitting right there? Degrees. So this should be what? Degrees. Everybody understand? And what is it then? It also, again, this gives you the what? The average, what? The average temperature over the interval what? 0 to what? 24 hours. So doesn't that give you the, don't we now know that the average temperature outside over that 24-hour period was 80 degrees? Yes? All right, now wait a minute. Because remember how I put one of those problems on the final exam where all I wanted you to do is figure out what the units on the answer are? Remember that? They do that on every AP exam. They give you a scenario, they give you some units on the function and so on, and you have to figure out what the units are on the answer without actually doing any math. All right, so I just showed you one way to figure out. How did I figure out that the units were degrees? How? By realizing that this gives you the what? The average value of whatever function is sitting right there. So the answer should have the same units as f, which is what? Degrees. That's one way to get the units. Now, if that's not good enough for you, let me show you a better way to understand what the units are. Are you ready? Are you ready? All right, let me explain, and then I'm done. And then you don't even have to work, because we'll only have 5 minutes left, and you can take a break. All right, so watch. Let me explain another way. Are you ready? This is really the way you should understand it, because I mean, that way I explained is fine too, but this way I think makes a little bit more sense. Are you ready? What are the units on 24 and 0? What are those? Those are times. So the units on those are what? Hours. So you got 1 over hours. All right, now what about this thing? That's area under the curve, right? Yes? And so if you think of, whether you're finding the exact area or the approximate area, the units are the same, aren't they? And so for simplicity, you can kind of think of finding the area with a bunch of rectangles. What are the units from here to here? Hours. What are the units from here to here? Degrees. And so when you find this area of one rectangle, or the whole area under the curve for that matter, what are the units on these? Degrees times what? Hours. And what is degrees times hours times 1 over hours? Degrees. So do you see another way or another reason why the answer to this turns out to be just degrees? Do you see it? Yes? Okay, you guys learned a ton today. And again, this is not easy stuff, I understand. But